You know that feeling? You want to really get up to speed on something new, something cutting edge. But you're just faced with this, like, mountain of dense research papers.
Yeah, happens all the time.
That's exactly where we come in. Welcome to the deep dive. We take those, piles of information, pull out the core insights, those real aha moments.
Right.
So you can get properly informed, but without drowning in details.
Exactly. Think of this as your streamlined path. We go straight to the source material you've shared and figure out what really matters.
So today, we're diving into the world of Earth observation. Pretty exciting stuff.
Definitely.
There's a new tool called Prithvi EO 2.0. It's a geospatial foundation model.
And it builds directly on the lessons from the first version, Prithvi EO 1.0.
Okay, geospatial foundation model. Let's unpack that a bit. What exactly is it?
Okay, so imagine an AI model that's already learned a ton by looking at vast amounts of satellite pictures, unlabeled ones. Instead of building a totally new AI every single time you want to, say, track deforestation.
Or like urban growth.
Exactly. You take this pre-trained model, like Prithvi EO 2.0, and you adapt it. It means less need for custom models for every little task.
So it's like a foundational understanding of Earth from space.
Yeah.
A base layer of knowledge.
You got it. It's learn the visual language, basically.
Okay, so the technical report we looked at digs into this 2.0 version, its upgrades, its potential.
Yeah.
But it also mentions something interesting, that even though these models, especially the ones using optical data, are getting a lot of buzz, they aren't actually being used that much in the real world yet. What's the holdup?
That's a really key question. The report points out a couple of, big hurdles with current foundation models.
Okay.
First off, Earth observation is all about change. Seasons shifting, storm impacts, long-term stuff.
Right, things happening over time.
Exactly. But a lot of existing models don't really capture that temporal dimension very well. They might just look at single snapshots or maybe tiny areas over long times.
So they're missing the story, the sequence of events.
Precisely. And the second big issue is this kind of disconnect, a gap between the AI folks building the models and the domain experts, the scientists or analysts who could actually use them.
The potential users.
Yeah. There's often not enough, deep validation to really build trust. And the code itself, it can be tricky for someone who isn't an AI expert to actually adapt it for their specific problem.
Reproducibility issues too, I guess.
That's part of it, definitely, making sure you can reliably get the same results.
Okay, so Prithvi EO 2.0 was specifically designed to try and fix these problems. How does it go about that?
Well, they tackle it head on. One of the big innovations is using something called transformer attention, but applying it explicitly in both space and time.
Transformer attention. Like the models used in language processing.
Kind of, yeah, but adapted for imagery. Think of it as the model being really good at focusing on the important bits of an image and how those bits change or relate across different points in time.
Like comparing photos side by side and spotting the key differences.
Exactly like that. It's a big step towards understanding the dynamic Earth.
That sounds significant. What else?
And then there's the data. It was pre-trained on this absolutely massive global data set. We're talking 4.2 million samples.
Wow.
Pulled from NASA's Harmonized Landsat and Sentinel-2 archive, the HLS data.
Harmonized, meaning they made the data from different satellites compatible.
Correct. And it covers a whole decade, 2014 to 2023, at 30-meter resolution.
So medium resolution, but global and over a long time.
Right. That scale lets it learn long-term patterns like seasonality, but also pick up on shorter trends within that, all using high-quality data.
And the model itself is big.
Oh, yeah. They developed two sizes, one with 300 million parameters and another with 600 million. That puts them up there with the largest models in this EO space.
600 million parameters. Just trying to wrap my head around that. That's like the model's capacity to learn complexity.
Essentially, yes. More parameters generally mean it can learn more intricate patterns from the data.
Okay, so huge data set, big model. How does it keep track of where and when all this data comes from? That seems critical for EO.
It is, and that's another really interesting part. Prithvi EO 2.0 directly incorporates metadata.
Like the coordinates and the date.
Exactly. Center, latitude, longitude, the year, the day of year. It gets encoded and fed into the model.
Wow.
They use learned weights, so the model figures out how important that metadata is, and they have this clever drop mechanism.
A drop mechanism.
During pre-training, they sometimes randomly hide the location or the date information, or both.
Why would they do that?
It forces the model to be more robust, to learn patterns, even if some metadata is missing, which can happen in real-world data. It helps it build a better internal map, you could say.
So it's not just seeing pixels, it's understanding the context, the where and when.
Precisely. And addressing that user trust issue we talked about.
Yeah.
They did extensive validation. They used GEO-Bench, which is a standard, rigorous framework for testing these models.
Okay.
And critically, they brought in subject matter experts, SMEs, people who actually work with this kind of data day to day.
So real-world testing by potential users.
Exactly. And they made it easier to use by integrating Prithvi EO 2.0 into a toolkit called TerraTorch.
TerraTorch?
Yeah, it's designed to help those experts fine-tune the model for their own specific tasks, classification, segmentation, even regression, making predictions.
Making it accessible, not just powerful.
That's the goal.
Okay, let's dig into that pre-training data a bit more. 4.2 million samples is huge. Where did it all come from?
So the core is that HLS data, Harmonized, Landsat, and Sentinel-2.
Right, NASA and ESA satellites.
Yep. Landsat 8 and 9, Sentinel-2A and 2B. The great thing about HLS is it gives you that compatibility with the long Landsat record, like 40 years. But with a much better revisit time because of Sentinel-2, you get coverage every 2 to 3 days on average.
Frequent snapshots. What kind of information are they using from the satellites? Just visible light?
They used 6 common spectral bands. You get the blue, green, and red, what we see.
Okay.
But also near-infrared, NIR, and 2 shortwave infrared bands, SWIR 1, SWIR 2. Those are really important for seeing things like vegetation health, soil moisture, things invisible to our eyes.
Got it. So a consistent set of measurements across different satellites. But how did they pick which images out of that massive archive? They couldn't use everything, right?
No way. They had a really careful sampling strategy. The main goals were diversity, cover lots of different land uses, different ecosystems globally, and quality minimize clouds and bad data.
How'd they ensure diversity?
They used external data sets. First, the Copernicus land cover data at 100-meter resolution to see what kind of land cover was in each standard HLS tile.
Like forests, cities, water.
Exactly. And also the Resolve ecoregions dataset to understand the ecological context. So for each tile, they knew the mix of land cover and the type of ecoregion. Then they started sampling tiles.
Based on those classifications.
Yeah, trying to get representation across classes.
Yeah.
They even deliberately oversampled urban areas because those can be complex.
Right.
And tiles that had a high mix of different land cover types, high entropy, to capture those tricky transition zones. And they made sure most ecoregions were included if they were big enough.
Sounds thorough.
Yeah.
And they split it for training and testing.
Yep, a 95% train, 5% validation split initially. Then came more filtering.
Filtering for what?
Quality, mainly. They wanted sequences of images over time.
Ah, the temporal aspect again.
Right. So for a chosen tile, they aimed for sequences of 4 images, each image 1 to 6 months apart, spanning that 2014-2023 window.
So capturing change over short to medium term.
Exactly. Then they chopped these sequences into smaller patches, 256 by 256 pixels, non-overlapping. And then came the really strict filtering. They looked at each patch. Too many missing pixels. Toss it. Too much cloud cover, based on the HLS quality flags. Toss it.
What about small gaps?
For small amounts of missing data, they use nearest neighbor interpolation, basically filling it in with the value of the closest good pixel.
Makes sense.
And to make sure they weren't just learning about one specific place really well, they limited the number of samples from any single small area.
Ensuring spatial diversity.
Correct. And crucially, they made sure none of the training patches overlapped spatially with the validation patches. No cheating.
Good practice.
And
any other cleanup?
Yeah, a couple more things. They removed some known problematic tiles over Greenland. And for areas that are really uniform, like big stretches of open ocean or desert, they subsampled them down to about 10%. Otherwise, the model might just spend too much time learning this looks like desert over and over.
Right, focus on the more varied areas.
Exactly. So after all that, they ended up with the final data set. 4.2 million training samples and about 46,000 for validation.
An incredible effort just to curate the data. So now the model has this amazing data set. How does it actually learn from it? What's the pre-training method?
They used an approach based on masked autoencoders, or MAE.
Masked autoencoders.
Okay. The basic idea is you hide parts of the input image, mask them out, and train the model to reconstruct the missing parts.
Like filling in the blanks in a picture.
Exactly. It forces the model to learn meaningful patterns and representations of the visual world to be able to do that reconstruction. The core architecture they used is a vision transformer, a VAT.
Right. VITs are everywhere now.
Yeah.
Did they have to modify the standard MAE or VAT for this Earth observation data?
Yes, definitely. Standard MAEV is for 2D images. Here, they're dealing with spatiotemporal data sequences of images.
The 3D data.
Sort of. They adapted the patch embeddings and the positional embeddings to be 3D instead of 2D. Although they mentioned the time dimension T was actually set to 1 in this implementation, but the framework handles 3D.
How do they represent position in space and time?
They generated separate 1D cosine encodings for time, image height, and image width, and then combined those into a single 3D positional encoding.
Okay, and the metadata location and date, how did that get plugged in?
That also used 2D cosine encodings. These were then added to the embedded image patches, but not just added directly, it was a learned weighted sum.
Meaning the model learns how much attention to pay to the metadata.
Precisely. And that drop mechanism we talked about, randomly dropping location or time during training, helps here too, making it more robust.
Got it. And they trained both model sizes, 300M and 600M, with and without this time location info.
Correct. 4 main pre-trained models resulted from that.
And the training itself must have been huge.
Oh, absolutely. They ran it for 400 epochs, full passes through the training data, using large-scale GPU resources on the Joule supercomputer in Germany. Specific batch sizes, learning rates, a major computational task.
Okay, so pre-training complete. Now, the big question, how good is it? You mentioned GEO-Bench.
Right, the benchmarking phase. This is where they really put Prithvi EO 2.0 to the test against the competition.
Who are they comparing against?
6 other prominent EO foundation models, ones people are using or talking about, plus their own earlier Prithvi EO 1.0.
And GEO-Bench provides the data sets and the rules.
Exactly. GEO-Bench is designed to be a rigorous framework. It has multiple data sets for classification, assigning a label to an image, and semantic segmentation, labeling every pixel in an image. These cover different resolutions, different sensors, different challenges.
And they followed a strict protocol. No tuning it just for the benchmark?
They were careful about that. The protocol involved hyperparameter tuning for first, finding the best settings for each model on each dataset using Bayesian optimization.
Okay.
Then, with those best settings fixed, they ran the experiment multiple times, like 10 times, with different random seeds to ensure the results were stable and reliable.
Fair comparison.
And to make it easier, they actually onboarded all the GEO-Bench datasets into their TerraTorch toolkit.
Streamlining the process.
Yeah. For the actual tasks, they use standard setups. A simple linear layer on top for classification, and common decoder architectures like UNet or UPerNet for segmentation.
Makes sense. Did they adapt the input data?
They focused on using the optical bands the models were originally trained on and resized all images to 224 by 224 pixels for consistency across models.
Okay, the moment of truth. What were the results? How did Prithvi EO 2.0 stack up?
The results were really strong. Looking at classification tasks across GEO-Bench,
Yeah.
Another model, DOFA, came out slightly ahead overall, but Prithvi EO 2.0, the 600 million parameter version with time and location info, TL, was a very close second. The 600M version without TL was third, so right up there.
Okay, very competitive in classification. What about segmentation? Labeling pixels.
That's where it really shone. The Prithvi EO 2.0 600 MTL model actually tied for the top spot with their older Prithvi 1.0 600 even model.
Interesting. The older one was still good at segmentation.
It was, yeah. Models like Dekur and Dino Resnets followed them, but Prithvi EO 2.0 was leading the pack.
So if you combine classification and segmentation performance.
Taking the overall picture across all GEO-Bench tasks, the two 600 MeBer Prithvi EO 2.0 models, with and without the time location embeddings, achieved the best combined performance.
That's a definite win then. A clear improvement overall.
A significant step up, definitely, especially compared to 1.0 when you look at the whole picture.
Did they see specific areas where 2.0 really excelled?
Yeah, digging a bit deeper, the Prithvi EO 2.0 models were particularly strong on the medium resolution tasks, the ones using Sentinel-2 data at 10 meters.
Which makes sense given the HLS pre-training data.
Exactly. They did really well on things like classifying complex land use areas, the mbig EarthNet dataset, and identifying crop types, MSA crop type, that really aligns with that multi-temporal global pre-training focus.
So the pre-training strategy seems to have paid off for those kinds of tasks.
It looks like it. The key takeaways from the benchmarking were pretty clear.
What were they?
1. The bigger, more diverse global data set for 2.0 really did lead to significant improvements over 1.0.
Okay. Data matters.
2. Bigger models generally performed better. The 600 NF parameter versions consistently beat the 300 MF ones.
Size matters too sometimes.
3. Incorporating those time and location embeddings generally boosted performance, especially overall. That context helps.
Right.
And 4, which is quite interesting, even though it was pre-trained at 30-meter resolution, Prithvi EO 2.0 performed well on some higher resolution tasks too.
Showing some versatility, adaptability.
Exactly. It wasn't just locked into its pre-training resolution.
Okay, so strong benchmark results. That builds confidence. But benchmarks aren't everything. What about real-world problems? This is where the SMEs came in.
Correct. This is the crucial next step, seeing if it actually works for practical applications guided by experts in those fields.
And TerraTorch made this easier.
Yep, the models were available in TerraTorch with example code for fine-tuning. They looked at 3 broad areas: disaster response, land use-land cover mapping, and ecosystem dynamics.
Let's start with disasters. What do they test?
Several key applications. First, flood mapping, using a dataset called Senfwan Floods 11.
How'd it do?
Prithvi EO 2.0 improved over 1.0. They saw about a 3.5-point increase in IOU intersection over union, a common accuracy metric specifically for the water class.
Which is ignored because water is often the minority class in floods.
Exactly, so accurately mapping it is critical. Then, wildfire scar mapping.
Okay.
Using a dataset they curated, Prithvi EO 2.0 again outperformed 1.0 with a solid 5.6-point IOU increase for the burn scar class.
That's a good improvement for identifying burned areas.
Definitely. They also tried mapping burn intensity, but the results there were a bit more mixed.
Oh.
Performance was generally lower across all models tested, not just Prithvi. The 300-meter Prithvi was comparable to a standard UNet, but the bigger version seemed to overfit.
Any ideas why?
They suspected it might be because the patch size used for the burn intensity task was smaller than the pre-training patch size, and maybe the UNet's strength and local details was an advantage there.
Interesting. What else in disasters?
Landslide detection using the Landslide ForSense dataset. This was interesting.
How is it?
The Prithvi EO 2.0 300 Meter model, especially when using a specific loss function called love as loss, actually outperformed standard models like UNet and UNet++ on the main metrics, MIOU and F1 score, when using the full dataset.
A smaller Prithvi did better.
In that specific setup, yeah. The 600 Ember version had higher recall. It found more potential landslides, but lower precision, meaning more false alarms.
Trade-offs.
But here's a cool finding. When they drastically reduced the amount of training data, down to only 2.5%.
Wow, tiny amount.
The Prithvi EO 2.0 600M model showed the most resilience. It maintained its sensitivity better than the others.
So the bigger model learned more robust features from pre-training, helpful when labeled data is scarce.
That seems to be the case. Visual check suggested the 300 MEMA had fewer false positives generally, but the 600 MEMA was better at still finding landslides, even with very little fine-tuning data.
Fascinating. Okay, so potential for disaster response looks promising with some nuances. What about the second area, land use and land cover mapping?
Right, things like mapping crops or general land types. They looked at 2 main scenarios. First, multi-temporal crop segmentation in the U.S.
Identifying the boundaries of different crop fields over time.
Exactly. Here, Prithvi EO 2.0, especially the 600M version, clearly outperformed a standard UNet baseline on MIOU and mean accuracy.
Good result for agriculture applications.
Definitely. The second scenario was in Europe, using a dataset called Sen4Map. This involved both land cover classification and crop type classification, again, multi-temporal.
Okay.
For the general land cover part, Prithvi EO 2.0 S 600 EMAs showed superior performance compared to Prithvi EO 1.0. A smaller 100 MEMA version was used for comparison here, and a baseline video model, Vivid. And this held true even when they used less training data.
Consistent performance.
And for classifying specific crop types within Sen4Map, both the 600 EMA and 300 EMA versions of Prithvi EO 2.0 performed similarly well, and both were better than the older Prithvi EO 1.0 and the Vivid baseline.
So strong results there too. You mentioned something about data differences.
Yeah, this is important. The Sen4Map data has different characteristics than the HLS pre-training data. Different spatial resolution, different patch size, even slightly different spectral bands available.
So the model had to adapt quite a bit.
Exactly. The fact that it still performed so well highlights its generalization capabilities. It wasn't just memorizing the pre-training data format.
Very encouraging. Okay, final category. Multimodal ecosystem dynamics. Sounds complex.
It involves using different types of data together. The first task was estimating above-ground biomass, basically, how much plant matter there is in forests.
How they do that?
They used data from a challenge called Biomasters, which includes both optical Sentinel-2 data and radar Sentinel-1 data. They actually created a hybrid model, Prithvi UNet.
Combining Prithvi's feature extraction with a UNet decoder.
Essentially, yeah, to handle the multimodal input. The results showed the model learned it converged, but its performance, measured by root mean square error, RMSE, wasn't as good as the winning model from that specific data challenge.
Any reason why?
They noted the test set might have had some low-quality Sentinel-2 data, which could have impacted it, but the key point was demonstrating Prithvi could be adapted to handle multimodal inputs like optical and radar together.
Okay, proof of concept for multimodal work. What was the other ecosystem task?
Estimating gross primary productivity, or GPP.
Right, how much plants are photosynthesizing.
Exactly. They use data from flux tower sites around the world, places that directly measure CO2 exchange. They fine-tuned Prithvi using the HLS optical data plus atmospheric data from a reanalysis product called MERA-2.
So combining satellite observations with atmospheric conditions.
Yep. And they compared it against a standard machine learning baseline, a random forest model trained on the same inputs, and also a version of the random forest given extra vegetation indices derived from the satellite data.
How did Prithvi do?
Impressively well. The fine-tuned Prithvi model significantly outperformed the random forest baseline, even the one that got the helpful vegetation indices as input.
Even though Prithvi didn't explicitly get those indices.
Correct. It learned to extract the relevant information directly from the HLS bands and the atmospheric data. The Prithvi EO 600 MTL model consistently achieved the best R-squared scores, showing a strong correlation with the actual GPP measurements.
That's a really strong result for ecosystem science.
It really is. It shows the potential for these models to integrate different data sources and capture complex ecological processes.
Wow. Okay, so pulling this all together from our deep dive, Prithvi EO 2.0 seems remarkably versatile.
That's definitely a key takeaway. It's a clear step up from its predecessor. It performs really well in rigorous benchmarks against other top models.
Right.
And importantly, it's shown success in a whole range of practical, real-world applications guided by subject matter experts.
From floods and fires to crops and carbon cycles.
Exactly. We're seeing a model here that can genuinely help deliver timely, accurate insights about land use, agriculture, environmental changes. The scale of what this could enable is, well, pretty mind-boggling when you think about it.
Yeah, the ambition is huge.
It really is.
And the report makes it clear how much effort went into that pre-training data set, the careful sampling, the quality control.
Absolutely critical. That plus the transparent evaluation process were key factors.
And they're sharing it.
Big time.
Yeah.
Their commitment to open science is clear. Both the 300M and 600M models are out there on Hugging Face.
Okay, accessible platform.
With a permissive license, and they're integrated into that TerraTorch toolkit so people can actually pick them up and start using them, adapting them.
Lowering the barrier to entry for researchers and practitioners.
That's the idea. Make it easier for the community to build on this work.
So as we wrap up this deep dive, it really paints a picture of the potential here, doesn't it? These adaptable geospatial foundation models. They can genuinely speed up how we understand what's happening on our planet, addressing huge challenges. Disaster response, land management, climate change monitoring.
The potential impact is enormous.
Maybe this has sparked something for you, listening in. Perhaps you're curious to check out these models yourself, maybe even contribute. It's a field that's moving incredibly fast, and it feels really important right now.